Welcome to Calculus 1. In this lesson, we begin with one of the most important ideas in mathematics, the concept of a function. A function is a rule that assigns exactly one output to each input. We usually write a function as y equals f of x, where x represents the input and y represents the output. A useful way to think about a function is as a machine. An input enters the machine, a specific operation is performed, and an output is produced. For example, consider the function f of x equals 2x plus 3. If we substitute x equals 4, we obtain f of 4 equals 2 times 4 plus 3, which is equals 11. The key idea is that every input must correspond to exactly one output. This property is fundamental to everything we will study in calculus. Let us look at another example. Consider the function f of x equals x squared. When x equals 1, the output is 1. When x equals 2, the output is 4. When x equals 3, the output is 9. When x equals negative 2, the output is again 4. Notice that different inputs can sometimes produce the same output. For example, both 2 and negative 2 produce the output 4. However, a single input can never produce two different outputs. If that happened, the relation would not be a function. Evaluating functions correctly is a skill that we will use throughout this course. Functions can be represented in several different forms. A function may be described verbally using board. It may be represented numerically using a table of value. Also, it may be expressed algebraically through an equation such as f of x equals x squared. Finally, it may be represented graphically using a graph. As we move through calculus, we will frequently switch between these representations. Each one helps us understand different aspects of a function's behavior. As important characteristic of every function is its domain. The domain is the set of all input value for which the function is defined. Consider the function x squared. Since any real number may be substituted for x, the domain consists of all real numbers. Whenever we encounter a new function, one of our first tasks is to determine its domain. Let us examine a more interesting example. Consider the function 1 divided by x minus 2. We know that division by 0 is undefined. Therefore, the denominator cannot equal 0. Setting x minus 2 equal to 0 gives x equal 2. This means that x equals 2 must be excluded from the domain. Consequently, the domain contains all real numbers except 2. This example illustrates an important rule. Whenever a function contains a denominator, we must exclude any value that make the denominator equal to 0. Now consider a function involving a square root. The function is the square root of x minus 3. For real value functions, the expression inside a square root must be greater than or equal to 0. Therefore, we require x minus 3 to be non-negative. Adding 3 to both sides gives x greater than or equal to 3. As a result, the domain begins at 3 and extends to positive infinity. Whenever a square root appears, checking the expression inside the radical is essential. In addition to the domain, every function has a range. The range is the set of all possible output value produced by the function. Consider the function x squared. Regardless of the value of x, its square is always non-negative. The smallest positive output is 0, which occurs when x equals 0. Therefore, the range consists of all real numbers greater than or equal to 0. Finding the range is often more challenging than finding the domain, but it is equally important. Graphs provide a visual picture of how a function behaves. For the function x squared, points such as 0, 0, 1, 1, and 2, 4 lies in the graph. Connecting these points smoothly produces a parabola. To determine whether a graph represents a function, we use the vertical line test. Imagine drawing vertical lines through the graph. If any vertical line intersects the graph more than once, the graph does not represent a function. If every vertical line intersects the graph at most once, then the graph represents a function. This test provides a quick and reliable way to identify functions from their graphs. Functions are powerful tools for describing the world around us. For example, temperature depends on time. We may write temperature as a function of time. Distance traveled by a car can also be expressed as a function. If a car moves at 60 km per hour, the distance after t hours is 60 times t. Another example is the area of a circle. The area depends on the radius according to the formula pi r squared. These examples show that functions are not merely mathematical abstractions. They are practical tools used through science, engineering, economic, and everyday life. Before moving on, Let us discuss several common mistakes. Students often confuse the domain with the range. They sometimes forget to exclude values that make denominator equal to 0. Others overlook restrictions involving square roots. Another common error is assuming that every graph automatically represents a function. Carefully checking this issue will help you avoid many mistakes later in calculus. Today, we introduced a concept of a function, one of the most fundamental ideas in mathematics. We learned how functions assign output to input, how to evaluate functions, and how to determine domain and range. We also examined graphs, applied the vertical line test, and explored several real-world applications. Functions form the foundation of calculus. As we continue, they will appear in every major topics, including limit, derivatives, and integral. In the next lesson, we will study mathematical models and explore how different types of functions can be used to describe and predict real-world phenomena. Thank you for watching, and I look forward to seeing you in the next lesson of calculus.